Hi there, this is Professor Shannon Gracey from Miracosta College. Today we're going to be covering differentials from the Larson and Edwards Calculus text. If you're interested in downloading the guided notebook, it is available at www.mathchick.net, mathchick. So today we're talking about differentials, where we can use differentials to obtain a tangent line approximation. We can estimate propagated error, and we can find the differential of a function using these formulas, differential formulas. So there's some pretty cool little things here, and this is the last section that we're going to cover of applications of the derivative, and then we'll be switching over to anti-differentiation. Okay, so let's go ahead and get ready to roll. Let f be a function that is differentiable at some input value c. The equation for the tangent line at point C is, do you remember? Dun, 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 dun. You can write it a couple of ways. You can say y would equal to, actually, why don't we do this? Thinking about, if you think about, I'll just do it in the corner here. Y minus y1 is the slope times x minus x1. Then we'd have y minus the function evaluated at c is equal to f prime at c, that's our slope, times, what will we have? Good, x minus c. So this just comes from, an introductory algebra equation, but we're using our calculus tools in there. Now, how else could we write this? If we added f at c to both sides, do you see we would get y is equal to, I'll just write it as this, f prime at c times x minus c plus f at c. So here we go. We call this the tangent line approximation or linear approximation of f at c. So let's take a look at this first example here. Our first example asks us to find a tangent line approximation, and that's denoted capital T at x, to the graph f at x equals x squared at the ordered pair 2, 4. So let's check it out. What might we need to find first? Beautiful. We might want to find the derivative, right? So f at x was equal to x squared. If you differentiate both sides with respect to x, what will happen? We will get, good, f prime at x is equal to 2 times x. Good so far? Awesome. So now if we want to find the equation of this tangent line, right, what would we need to do? It's at the ordered pair 2, 4. All right, so let's figure out now what is the slope when x is 2. So f prime at 2 is equal to 2 times 2, which is 4. So that will serve as the slope of our line. So then we'll get y minus, good, 4 is equal to our slope, which is 4 times x minus 2. So let's see how everything matched up. The slope was this 4 over here. Our y value when x is 2 was 4, so that's where we got that guy. And we're interested at x equal to 2. So we used x equal to 2 in both the derivative function and then to make the equation of our line. So now if we go ahead and we isolate y, do you see that we will end up getting 4x minus 8 plus 4, and so at the end of the day we'll get y is equal to, good, 4x minus 4. So now we're going to write it down here. Instead of denoting this as y, we're going to denote this as t at x. So that will end up giving us 4 times x minus 4. So now let's take a look at this chart here. I'm going to grab my graphing calculator and I'm going to do a few things here, all right? So first I'm going to put in our original function, which is, if you recall, it was x squared, okay? Now the derivative function is going to be the derivative for when x is equal to x. I'm also going to put in the tangent line that we found for when x was equal to 2. So that's 4 times x minus 4. Good so far? Okay, so let's take a look at these guys. I'll just do a zoom standard. So the blue graph was the original function, the green graph is the derivative function, and the hot pink graph is the tangent line for when x is equal to 2. So I'm going to go ahead and let's go ahead and take a look at values that are close to 2. So let's see, I'll just kind of see. Actually, I don't want to be too far away because I want to show you how they trend differently. And so here's a little snapshot of what we've got going on here. And then we'll start getting our values. All right, so now let's take a look at these different values that we're going to be finding. I'm just going to go to second, calculate value. And we'll calculate 1.9. And what we're looking to find is the first graph, which is x squared, so we get 3.61. And then the second graph, which is, or not the second graph, it'll be the third graph. So I'm going to tab over to that purple one, and we get y is equal to 3.6. Continuing, we will have, now we're interested in 1.99, so you don't need to hit it again, the second calculate, you can just hit your next value. And we'll get, for the pink graph, we'll get 3.96, and then for the green, or the blue graph, we'll get 3.9601. Alrighty, now let's take a look at what happens exactly at 2. So for this one, we don't really need our calculator, but we can go ahead and use it. So for the blue graph, the original function, we of course get 4. And wow, we get 4 for our tangent line approximation. So then, next up, 2.01 for both, and then 2.1. All right, so we want our blue graph 4.0401 and then 4.04. So 4.0401 and 4.04. And then lastly, when we do our 2.1, we will get, So our purple is 4.4, or the pink is 4.4, and the blue is 4.41. Okay, so let's kind of check this out. And it's really very easy looking at the graph, especially if we kind of adjust the window a little bit. So let's take a look at this graph, and we can look at it close up. But do you see that right at x equal to 2, so if we just put 2 again, all right, basically what happens is, let's do a table. Whoops. So for x equal to 2, I'll go ahead and look at the table. Do you guys see? Oops, we want to start at 2. Second table set, table start. We'll start the table at 1.5. No, you know what? Let's start the table at we will start it earlier. Let's start the table at -2, okay? And then we'll have the change in the table be 0.5. And so let's take a look at what we get. So second table. So check out what's happening here. I'm going to copy this so we can discuss it more. Oops. Oops. All right, I'm going to put our little table down here so we can check out what's going on. And then I'm also going to put the graph here as well in a moment. But do you see, I'm going to put the little hand tool here. Do you see that right when x is 2, and remember we were at the ordered pair 2, 4. So the first one, the blue, is our original function. The second one is the derivative function. And this third one, the pink one, is the line that's tangent to this blue curve at x equal to 2. All right, so basically what you're going to see here is this. You're going to see that exactly when x is 2, do you see that these outputs are all the same, right? So we get a very good approximation to the slope of the graph, basically, right exactly when x is 2, right? So at this input value here, all these output values are the same. But look what's happening as we move away from x equal to 2, right? So here are the actual output values, right? Here are the derivative outputs, and here are the tangent line outputs. So here, what's happening is we get further and further away from our actual graph, okay, our actual graph. So now we're focusing on the blue and the pink. So we get further away from our actual graph when we're further away from x equal to 2. So here, do you see you have 4 and a -12, right? a little closer to 2, you've got a 1 and a 0. That's closer. Then you've got 2.25 and 2. And right here, right at x is 2, this is a perfect approximation for the y value of the original function. Okay? So let's take a look at the graph as well. All right, so let's go to, I'll just go back to Zoom Standard. And actually, what I'm going to do, so that we don't get confused, I'm going to take out the graph of the derivative for right now, and just do the 2 graphs. And then I'll start the window at -5 to 20. And I'll do the same for the actually we'll go -5 to 20 for the y values, and the x values will just go until we get to 5. And let's see what this looks like. Okay, so what we'll do here is this. We'll check out our graph. Put it over here. All right. So here we go. Let's do this because I wanted to show you doing a problem that we had done, what we're kind of looking at here. Okay, so here we go. Basically, what we're finding is this, all right? We're finding that at values that are very, very close to 2, we get a very good approximation for the y values of our original function when we use t at x, all right, the tangent line function, when x is 2. Good so far? All right, so here we go. Let's think about this and draw on our picture what we have kind of going on. So here, if we look at our graph, and this is from, you know, the other ones where we had our f of x was equal to x squared, and then we had, let's see if I can find a pink one, and our t at x is equal to 4x minus 4. All right, so this is basically what we're going to be looking at. If we take a look at some actual values here, so if we take a look at this tangent line, and if we think about what's happening when we're right at this ordered pair where they're equal to each other. So this is right here, the ordered pair 2, 4. Okay. Now let's see what's happening. We have our tangent line, and our tangent line works pretty darn well. And let's go ahead and draw this slope triangle here. Good so far? Just kind of a slope triangle here. And do you see, let's take a look at these lines here. So this, I don't want to do an ordered pair, but this it's not cooperating. I'll highlight it. So this length right here in the green is actually dy, the differential of y, okay? The differential of y is equal to f prime at x times dx, which is the differential of x. So this green highlighted length is all of this, okay? Now over here, this other length right here, the whole thing is the actual change in y. So this one here represents delta y, okay, which is literally equal to f at x plus delta x minus f at x. And this represents the actual change in y. Now over here we have our estimated change. So the dy, the differential of y, is our approximated change. In y. And so what that means is that it works really well for when we have domain values near. Good. This works well when we have domain values near 2. Close to 2. And what is working well? This means that we can use our t at x equal to 4x minus 4 to find function values. So f at x, I'll say outputs when x is near 2. All right, so that's pretty much the whole key of this business. All right, so this tangent line, this pink tangent line that, remember, we made using that x value of 2, works very well when we are close to 2. So, and if we take a look here, this bottom part here is the change in x. So your actual change is delta x, and we let that be equal to dx. Good so far? Okay, we'll get to more of this later. So basically, to make a long story short, at values which are very close to x equal 2, t at x provides a good approximation of f at x. Okay? All right, so hopefully you got sort of a gut feeling, a visual about this. And let's take a look at, this other problem. So in this second example, we're letting f at x equal to 6 minus 2x squared, and we want to compare the actual change in y and the approximate change in y when x is equal to -2 and when the change in x is 0.01. So what do we need to do? F at x is equal to 6 minus 2x squared, right? We need to find what is delta y and what is dy, right? So delta y is f at x plus delta x minus f at x, but we just said that delta y can be found as f at x plus dx, right? Because delta x equals dx minus f at x. So delta y, plugging that stuff in, is going to be equal to f at -2 plus 0.1 minus f at -2. So delta y will equal to f at -1.9 minus f at -2. So if we go have 6 minus 2 times -1.9 squared equals -1.22. So that's our actual change in y is -1.22. Now our approximate change in y is actually something where we'll need the derivative, right? So we will have f prime at x is equal to -4x. And so remember over here we have our dy equals f prime at x times dx. So dy will equal to f prime at -2 times 0.1, and we'll get dy is equal to, let's see, f prime at -2 would be +8, and 8 times 0.1 is 0.8 at 0.8. So there you have it, the approximate change in y. Oh my God, did I really just do that? Fucking hate differentials. So delta y will be equal to, so let's see, our f at -1.9 was -1.22. And then we're going to subtract from that f at -2, which we can just do in our head. That would be 2 times 4 is 8, and 6 minus 8 is -2. So this will be adding to, so the actual change in y is going to be positive 0.78. Now, where'd our function go? F at x was equal to 6 minus 2x squared. Differentiating, we get f prime of x is negative 4x. So recall that dy from the right side there is equal to f prime at x times dx, which is going to give us dy equal to f prime at negative 2 times 0.1. So dy in comparison is going to equal to, let's see, f at negative 2 is going to be positive 8. So we'll get 0.8. So those guys are pretty close. This again is our approximate change in y. And over here we had our actual change in y. Okay, so very close, as you can see. Alrighty, so now let's go on to error propagation. With error propagation, the main idea here is that there's always some kind of error, whether it's error in your measurement, whatever you have. So there's like a measured length, right? And the actual length, which would be the measured length plus or minus the error. And it could be the measurement tool or it could be the measurer. So basically what we have, if we tie it back in, we have our f at x plus delta x. All right, so the exact value is this whole thing. The error is the change in x over here. And so that's going to be, if you subtract that from f at x, okay, which is the, what do you think x would be? Good. X would be the measured value. And that's all equal to the change in y, which is called the propagated error. And of course, we often will approximate delta y with dy. So when we are calculating differentials, right, what we're doing here is pretty much like we did in that prior example, right? So when we're calculating our differentials, you have to remember that delta x is supposed to be small in order to be able to approximate. So when delta x is small, right, then the actual change in y can be, which is exactly equal to f at x plus, I don't know, let's x plus delta x minus f at x. And that can be approximated by delta y is equal to, is approximately equal to dy, which is f prime at x times delta x. Now, and delta x is approximated by dx, so delta y equaled approximately dy, which is f prime at x times dx. Okay, so far? So let's find these differentials. So the actual derivative, right, of y equals x squared is? Good. Y prime is equal to 2x. Now, the differential would be what? Good. It would just be dy is equal to 2x times dx. See? Not bad at all, right? Now, over here, the derivative here, if you recall, is equal to 1 over 2 root x. And what's our differential? dy is equal to 1 over 2 root x times dx. Continuing. Good. Y prime is good positive 2 sine at x, because the derivative of a cosine at x is negative sine at x. And the differential will be dy equals 2 times sine at x times dx. All right, what about this guy? We've got to do a little more work there, right? So y prime is going to be the derivative of the first, which is 1, times the second, which is 1 minus x squared to the 1/2, plus the first times the derivative of the second, which is going to be 1/2 times our something to the negative 1/2, and the something here is 1 minus x squared, and the derivative of that is, good, negative 2x. So, continuing to simplify, y prime is going to be, let's see, we can divide out a 2, and we can factor out a 1 minus x squared to the negative 1/2, and we'll be left with 1 minus x squared to the 1, right? And then minus x squared. So y prime is going to be 1 minus 2x squared over the square root of 1 minus x squared. So our actual derivative y prime is 1 minus 2x squared over the square root of 1 minus x squared, and our differential will be dy is, good, 1 minus 2x squared divided by the square root of 1 minus x squared times dx. Good so far? Awesome. Alrighty, so now this error propagation works well in examples like this next one, example 4. So here, what we want to find out is, we want to find out, first of all, analyze the problem, and then secondly, we want to figure out, what our differential is that we need to find and all that. So measurements of the base and altitude of a triangle are found to be 36 and 50 centimeters respectively. So the possible error in each of the measurements is a 1/4 centimeter, And we want to use differentials to approximate the possible propagated error in computing the area of the triangle. So what should we start out with? Good. Maybe we should kind of, relate the variables in some way, right? So it's not a related rate problem, but, you relate the variables to figure out what you have going on. So the area of a triangle, right, is equal to the half times the base times the height. So now, let's check out what we know, right? Let's identify what we know and what we need to find out. So we know that the base was equal to 36 centimeters, right? And we know that the height was equal to 50 centimeters. And we know that the error in each measurement is a 1/4 centimeter. So that means the differential dB is equal to dH, which is plus or minus 0.25 of a centimeter. All right, and we want to find what? Good, dA. All right, so we need to do what, do you think? Find dA. So when we are finding dA, let's write our area formula again. Half times base times height, right? So here we're going to end up with what? If we differentiate both sides with, why don't we just do it with respect to x? It's really not going to matter, okay? It's not totally proper, all right, but don't tell anyone. Shh. So if we differentiated both sides with respect to x, let's see what happens. We're going to get dA dx, right, because it's implicit, is equal to 1/2 times. Now, we're going to have h times dB dx, I'm using the product rule, plus b times, good, dH dx. But look what happens. It's really awesome. If you multiply both sides by dx, right, look what happens. All the dx's go away, and you're just left with these differentials. So you get dA is equal to 1/2 times h dB plus b dH. So you can go ahead and you can memorize differential formulas, but if you just differentiate both sides with a variable where you'll have to do implicit differentiation for all the variables, or all the variables, then you'll be fine. You just multiply out that excess variable. So here we got our differential. So now we found dA, and so actually I think that was number 3 in this case. So now why don't we plug everything in. So when we plug everything in, we have dA equals, 1/2 times h dB plus b dH. And if you recall, we have a lot of those things. What was h? Good. H was 50 centimeters. I'm going to leave the units out for the moment. And then dB was plus or minus 1/4 centimeter. And then we're going to have plus B, which was 36 times plus or minus a quarter centimeter. So now let's check out what we've got. Do you see we can factor out, if the plus or minus freaks you out, just leave it out until the end. Let's go ahead and just factor out that plus or minus 0.25 for the moment and multiply in through with that 1/2. So we'd end up with 25 plus, what's that going to be? 18. So dA will be plus or minus 0.25. 25 plus 18 is 43. And then we'll end up with 43 times a quarter. $10.75. So the differential of A is plus or minus 10 point, did I say 75? Yep, 10.75. All right, so now why don't we kind of write down a solution or a conclusion here. So when we write our conclusion, you know, the possible propagated error, the possible propagated error in computing the area of the triangle is plus or minus 10.75 centimeters squared. And isn't that really crazy? I mean, it was only off, right, by a quarter of a centimeter. And look what happens with the area, how far off the area can be. So propagated error is really important, especially if you're going to go into, engineering or something like that, right? Okay, so now let's take a look at this next example. So we have a surveyor. And so again, we'll figure out what the heck's going on, right? So he's standing 50 feet away from the base of this big tree, right? So we've got our tree. This is why I was not an art major. Right, and then we've got, you know, the grass. And then here's the guy, right? This is going to be 50 feet away. Okay, so let's go ahead and write that in. This measure right here is 50 feet. Okay, and he's measuring the angle of elevation to the top of the tree, right? So if you go from here, our angle of elevation to the top of the tree, so of course, you know, the evil plan is we make a triangle here. And so this angle of elevation is 71.5 degrees. How accurately must the angle be measured if the percent error in estimating the height of the tree is to be less than 6%? So let's go ahead and get started. So now we need to take a look, and we need to not only find our form, find the differentials, because we weren't given the measurement error, right? What were we given? Let's think about what we were given. Good. So this you see would be the height of the tree, right? And so dH over H times 100% is equal to our percentage error. Relative error can be a little easier to work with. So the relative error is just going to be dH over H, which is equal to 0.06. So I think that'll be better to work with. So now we need to find dH over H. So let's go ahead and find our differentials. And when we find our differentials, we have tangent theta is equal to H over 50, right? But we want this in terms of H. So isolating H, we would get 50 times tangent theta. And our differentials will be dH is equal to 50 times secant squared theta, d theta. So now going back over to look at our relative error. Remember that dH over H was equal to 0.06. So we have dH was 50 times secant squared theta, d theta, over H, which was 50 times tangent theta. And that's got to equal to, remember it's really plus or minus 0.06. We'll do the plus or minus at the end. Okay? So, isolating d theta, we will end up with the 50s will divide out. We'll have 0.06 times tangent theta over secant squared theta. Which gives us d theta is 0.06 times sine theta over cosine theta for the tangent function, and then times cosine squared theta over 1, because remember secant squared theta is 1 over cosine squared theta. And so we can divide out one factor of our cosine theta. And so we'll get d theta is equal to 0.06 times sine theta times cosine theta. So let's plug in the numbers we have. Come back up here. So we'll have d theta is equal to 0.06 times sine of our 71.5 degrees times cosine of 71.5 degrees. So d theta will be approximately, let's get out our calculator, make sure that you're set in degree mode. So if we go to mode, see that we're in degree, so we're good there. All right, so let's see what we get. We'll get 0.06 times sine of 71.5 degrees times cosine of 71.5 degrees. And we get 0.018 approximately. And that is going to be in our error in terms of degrees, right? So we can be off by 18 thousandths of a degree when we measure, right? So let's just write our conclusion. I have no idea what step we're on. 5 million. So 5 is our conclusion. So the angle must be measured within 0.018 of a degree. And when I say within, it includes the plus or minus. Okay? All right. So that takes care of that guy. All right. So now this is a real fun application of differentials. They can be used to approximate function values. So to do this, we use this formula here. And so basically it's the, I'm going to rewrite it down here. My spacing got off. Sorry about that, guys. So this is our formula that we use here, and it's really pretty cool. And so the beauty of this is we can end up using differentials to estimate these function values. And before, you know, everybody had the use of calculators and whatnot. This is what they had to do. So let's just clean this one up a little bit. So here, so that you know what you're working with. Basically, remember that f at x plus delta x minus f at x is exactly equal to the change in y, actual change in y, right? But we can approximate this with dy. And what is dy? Good. dy is f prime at x dx. And so isolating f at x plus delta x, we would have, this can be approximated by f at x plus f prime at x times dx. Okay, so far? So looking at the cube root of 28, so I'll do this one, that one over here. All right, that's part A. The cube root of 28. So what we want to do is we want to figure out the closest perfect cube that we have to 28. So do you guys see that this could be written as the cube root of, good, 27 plus 1? So now what we found is that, I'll just do it all on the sides. So if you have x plus change in x, right, you'd have x is equal to 27. F of x, of course, is equal to the cube root of x. And then we have dx is equal to 1 because 27 plus 1 is 28. Right? So here we go. We would get that the cube root of 27 plus 1 is approximately f of x, so f of 27 plus f prime at 27 times dx. So our f prime would be what? So this would be the cube root of 27, and then plus 1 over 3 times the cube root of x squared, right, for our derivative. And then our dx was times 1. So this will give us 3. Oh, sorry. F prime at 27 would be, oops, 1 over the cube root, 3 times the cube root of 27, and then we would square that result. So this would give us 3 plus 1 over 3 times, good, 3 squared times 1, which will give us 3 plus 1/27, which is 82/27. And 82/27, you'll see, you can kind of check it out, is approximately, so 82 divided by 27 is approximately 3.037, and 27 raised to the, or sorry, this would be, clear this, 28 raised to the 1/3, that's the cube root of 28, is 3.0365. So isn't that kind of groovy? All right, so let's try this next one. This next guy is sine at 0.01. So you see, we could say, oh, okay, this is sine at 0 plus 0.1, and that'll be approximately, so what's our function? So if we go on the side, f of x is sine at x, right? Let's go ahead and do the derivative in general. F prime of x is cosine at x. X is 0. Dx is 0.1. And I think then we'll have everything. So that'll be approximately, I'll do it down here, sine at 0 plus cosine at 0 times 0.1, which gives us 0 plus 1 times 0.1, which is 0.1. So now let's see how this approximation worked out. So the original was sine of 0.1. Now be careful, I'm going to have to switch back into radian mode. Okay. So we have sine of 0.1 was the original that we're trying to estimate. It's 0.0998. And then isn't that pretty close to 0.1, which is what we got? All right. Awesome. Okay, well, have a fabulous day. I'll see you next time, sort of.